And what we're going to do with a comparison test is, if we're looking at one series, whatever it is, and I just have A's and B's up here, it doesn't matter what we call them, right? And there's infinity. We're going to compare one to another. We kind of did this a little bit with the P-series test when we kind of reduced like, n squared over n to the fifth plus 1. And the 1, yeah, it matters, but it's not going to matter in reference to infinity, okay? So what we really compared this to is that we can break it down to like 1 over n cubed. Work with that. So we kind of did a little bit of the comparison. And what we're going to do is look at our series here. And what I have is B converges, then A converges. So it depends on which one's bigger or smaller. Now think about this. If this is the outside when this converges, then of course anything smaller would have to converge. Remember we've talked about once it diverges, it's gone. Okay, so if you're going to say this outside one converges, anything inside has to converge. Okay. Well, if we're going to say the smaller one diverges, then of course anything after would have to diverge. It's not going to turn around and come back and converge. Does that make sense? If this guy, and I wrote these statements, but think about this, if this guy diverges, we don't know anything about this one. It could have been converging to a point and all of a sudden diverged. But it does matter if the smaller one diverges, because then it's gone the rest of the way. Okay with that? So we're going to look at some series, and what we're going to do is compare them to a simpler one. What would be easier for us? Okay? Similar to what we did before. So we're going to have the sum. This thing goes from 1 to infinity. And let's go 3 over 2 to the n plus 1. Now let's think about what we've talked about before. If we're going to compare to something, what doesn't really matter up there? Plus 1 doesn't really matter. What else doesn't matter? The 3. So this would just be 3 times the whole thing, right? So if it was 3 times a convergent, it converges. If it's 3 times a divergent, it diverges. It's not going to change anything, okay? Yeah, this is important, but at infinity, it's not really changing anything. Adding that 1, okay? So when we say something doesn't matter, we're just saying in reference to infinity, it's not going to matter. It's not important for that, okay? Yes, it can change values, but it's not going to change a convergence or a divergence. That's the idea, okay? So what I want to compare this to, I'm going to compare to the sum of 1 over 2 to the n. Kind of get me a more simplistic one. Doesn't mean that it's going to be easy, but it's definitely got rid of a couple things that the other one had. Okay? Now, what does this look like that we've done?
That looks like a
Looks like a geometric, because you could, the 1 to the n would just be 1, right? So we could actually rewrite it as 1/2 to the n. Everybody okay with that? All right, so this would be geometric. R equals 1/2 converge. I'm just trying to determine convergence or divergence, but one of the things that I would suggest you do, especially in your notes and even like in your homework, don't just say convergence, practice writing down why, because then when you look back at it, you're like, all right, why did I say that converged? All right, I'm seeing geometric, R's 1/2, it's going to kind of help me get used to the different ones. Right? And you can do any kind of little shorthand notes that you want. You can change anything. All right, so since this converges, since the sum of 1 over 2 to the n converges, then the sum of 3 over 2 to the n converges. Again, we're just doing 3 times that convergent sequence. And it's a good idea to help you because you're going to have to explain some things as far as why you're doing something. Write this down. Hey, if this does, then this has to. And like I said, you can use whatever shorthand notes you want, but just describing what you're thinking. Okay? So now I know that converges. So now let's take a look at 3 over 2 to the n plus 1 compared to 3 over 2 to the n. So this is the guy I'm concerned about. I've got both of them written up there. Which one is the bigger one of the two? Careful.
Yeah, you're automatic. Smaller.
Yeah. That's the bigger one. There you get fractions. The bigger denominator is going to make it smaller, right? Like a 1/5 to a 1/4. So it looks a little tricky there. All right. So since this one is less than this one, and we said that converged, so that means that this outside one's converging. Everything inside has to converge. Does that make sense? I determined the outside one. This was the bigger one. It converged. So anything smaller, and we agree, hey, that's smaller because the denominator's bigger. Okay. Since I know that, then the sum of 3 over 2 to the n plus 1 converges. Now, I don't think necessarily every time you do a comparison series that you need to do all the writing, but I think it does help in the notes. You're kind of explaining what's going on, and when you look back, you know how you made the transition from one step to the other. Okay. So, again, we went to a nice simplistic one, all right, that we kind of know. Well, why does it converge? Stated why. Help us remember. Well, if that does, this does, because that's just 3 times. Not going to change anything. And then now we're comparing this guy to our original, what we had. Let's go with this one. N goes from 1 to infinity. 1 over n squared plus 2n plus 2. All right, what's something I can compare that to that's nice and simple? 1 over n squared. Because the 2 is definitely not going to matter out there. And the 2n really doesn't. Remember, we've seen before, if I'm adding 2n, doesn't really matter. But if I'm multiplying by 2n, it does, because that's going to create an exponent, right? A different exponent. So I'm going to compare to 1 over n squared. So there's my simpler looking sequence, and now I'm going back to the stuff that I previously learned. All right, would 1 over n squared converge or diverge? And if you're thinking of which one it does, you got to also remember why. Why?
Because the P is more than
Oh, yeah. Converge. P equals 2, which is greater than 1. P series. And if you're writing P, that's enough to remind you that was a P series. Just like technically we don't need geometric. R would be enough to remind me it's geometric. It just depends on how much you're remembering. Okay? So we know it's going to converge because P is 2. This would be one you could also do, you could integrate that. You could do an integral test. Right, so remember, you have all those others that you can do to figure out. You're not limited on only a specific one will work. That's not always going to be the case. Okay, so now we're going to look at this. Tell me about 1 over n squared plus 2n plus 2 compared to 1 over n squared.
the one that's done squared.
There we go. This one's bigger. Does everybody agree with that? Because that other denominator is going to be larger, right? No matter what it is. Okay? So since This bigger one is on the outside, and it converges. Everything inside is going to converge. But then the sum of 1 over n squared converges. Not 1 over n squared. 1 over n squared plus 2m plus 2. Whole thing. There we go. My comparative piece. Okay there? This one. Limit. N goes from 1 to infinity. 1 over 2 to the n plus 1. What can I compare that guy to? I've heard both. I can compare 1 over n, and I heard 1 over 2 to the n. Both are correct. Okay? But let's think about this. 1 over 2 to the n.
I meant to say 1 over 2n. I don't know why I said 2 the n.
Oh, you were right, though. I said it wrong. 2n. Couldn't I make this 1/2 times 1 over n?
Yeah.
Okay, so I'm not going to disagree and say you can't use 1 over 2n. You certainly can. Okay? Either one of these will suffice for what we're trying to do. It's not going to matter. It's still ignoring this guy because it's not going to change anything in infinity. That's the idea. Okay, so 1 over n or 1 over 2n, either one works fine. I don't care if you leave the 2n or not on yours, but what does it do? Converge, diverge? What? There, diverge, harmonic. What's another reason it diverges? I mean, that's correct. Nothing wrong with that. All right. P series, P's 1. What else could you use? Integral test. Okay. So you had a couple things there on this one. Right? And any of them would be correct. Okay. There's not a specific one you have to do. You've just got to state why you're saying that diverges. Whatever legitimate reason you're using for that. Okay.
Wait, 1 over n converges? I mean diverges? I thought it...
1 over n diverges. That's the harmonic one. Or you can do the integral test. We did it with the integral test too yesterday. You did that with ln of n or ln of x.
I got the graph right here, and it looks like it converges to 0.
But the sum doesn't.
Oh.
You have a horizontal asymptote at 0. It never reaches it. So, all right. So this thing diverges. Here's a nice thing on a comparison test about it diverges. I've said it a few times. Once it's gone, it's gone. Once it's gone, it's gone. So if you get it diverging. The adding 1 on the bottom or multiplying the whole thing by 1/2 isn't going to change the fact that it diverges. It's not going to change that.
Wait, hold on. Is it 1 over n bigger than 1 over 2n plus 1?
1 over n is bigger than 1 over 2n plus 1. All right, but here's one of the things that you can do. This diverges, right? Okay, now I just flipped it.
So 1 over n diverges, but 1 over n squared converges.
Correct.
All right.
1 over n squared converges, 1 over n diverges. Test.
Oh, because the p-test.
Yes.
Okay. All right.
Everybody okay there? Now, this is a little tricky here to kind of flip this around. I agree with that. Okay. But what we've stated is if you multiply, and you agreed with this, if you multiply a convergent series by something, it still converges. If you multiply a divergent series by something, it still diverges. It's not going to affect that. Everybody agree with that? Okay. So, if I want this to flip around and I throw a 3 here, now this is the bigger denominator, right? Makes it the smaller one. But all we did was 1/3 times 1 over n. So we took a third of a divergent series, which is still going to diverge those pieces around. So then it is setting up. So now that inside one's diverging. But the nice thing to remember is, once you're gone, you're gone. Because you can play with numbers and make it adjust. Because we're talking about out there at infinity, and multiplying by some constant out there isn't going to change the fact of what we're at. That part's not going to be affected. It will definitely change these inside ones, these lower ones. Say the value is 1 to 1,000, but it's not going to change way out there. It's not going to affect the overall. Okay. All right. Limit comparison. The comparison series or comparison tests are two that I really like because I can come up with something a lot of times that just looks a lot simpler to kind of work with. Okay. Limit comparison works a limit into it. We're still going to come up with something. Limit comparison test, if you're really good and comfortable and like limits, which a lot of time you do because it's one of the first things we did and it keeps coming back. Okay? So then this becomes a test that you might like. The limit as n goes to infinity of a sub n over b sub n equals L, where L is finite and positive. Where L is finite and positive. So we're going to compute a limit. We're going to get a value. 2, 1/3, 5/4. So just some value, whatever that value is going to be. Okay. If it's finite and positive, then either the sum of a sub n and the sum of b sub n both converge, or both diverge. So we're going to take our series, we're going to come up with something smaller. Okay. We're going to look at something smaller or easier or simpler, compare it to there, and work the limit. So let's look at this. N goes from 1 to infinity, 3 over 2 to the n minus 1. It's a pretty similar to what we had on the first one. I think I had a plus 1 on the other one. Doesn't matter. So my comparative piece would be the sum of 1 over 2 to the n. Kind of what we saw before, right? Which would be the same as 1/2 to the n. There's that geometric r's a half converge. Everybody agree? So this thing converges. R equals 1/2. Okay. So if I compute the limit, and the limit's finite and positive, then that means this guy converges. I've got to show that that's what happens with the limit. Now, a lot of times there's confusion. How do we know which one to go on top? It really doesn't matter. Okay? So let's say you put A on top and B on the bottom, and let's say the limit's 5. Well, if you flip them, the limit would be 1/5. Still finite and positive. So it's not going to really make a difference which one you put on top versus which one you put on the bottom. It's not going to change anything. So let's go to limit. N goes to infinity. I'm just going to put this one on top. No particular reason other than I felt like it. But I'm trying to get this limit, and this limit would be 3. If If you're not the best with dealing with these complex fractions, maybe switch it around. Maybe we can do this, 3 over 2 to the n minus 1 times 2 to the n over 1. Invert multiply, looks a little better. Now we're at infinity. Those two are canceling. The minus 1 isn't going to change anything. Okay? So, in other words, maybe we have this. And I don't know. It's going to 1, right? So this is going to 1 times 3 over 1, 3. 3 is definitely finite and positive. Okay. So we're good here. Finite positive, which means this converges. And so again, I said it before, let's make sure you understand, if I had flipped those two, well, you make sure it doesn't matter which one's on top. If I had flipped these two initially, my limit would have been 1/3. Still finite and positive, still working. Okay? So it doesn't matter which one's on top. Let's look at this one. Let's go, n goes from 1 to infinity, square root n over n squared plus 1. Compare to, what's a good one to compare it to? Close. Not 5 halves. 3 halves, because we're going to take a half away. 1 over into the 3 halves. There we go. So that plus 1 isn't going to change what we're doing. I got a half on top, 2 on the bottom. I can reduce it to 1 over into the 3 halves. Now, what does that guy do? Why?
Because the piece here was just right up there.
All right. Converge. P's 3 halves greater than 1. And the nice thing, stuff like this, geometric P series, the more of these tests you do, you start reusing a lot of those others. You get used to them. Now let's go for our limit. If my limit's finite and positive, I'm good to go. So we're going to have n to the 1/2 over n squared plus 1 all over 1 over n to the 3 halves. Again, doesn't matter which one you put on top versus bottom. Okay. This is correct. Nothing wrong with this. Sometimes it is easier to see if we switch it to multiplication. So if you need to, or even think you need to, I would suggest going ahead, invert, multiply, get that in a little better form for you. Okay. Now, what does that limit equal? Yeah, we can simplify it to that. Still got to do the limit, though. I agree with you, though. That's n squared over n squared plus 1. What's the limit? 1. Same powers, top and bottom, both square. Leading coefficients 1 over 1. There we go. And that's finite. And it's positive. So that means this guy converges. Now I can't really say which one's better. It's more of a preference. Comparison versus a regular comparison versus a limit comparison. The nice part about either one of them is you get to work with these simpler ones. Okay? So you get to ignore a lot of the other stuff that's going on that a lot of times confuses us. I mean, this guy does not look good at all. When you're able to combine the exponents, it sure looks a lot better. Something like that. All right, so you can make some of those more complicated looking ones look better, and then we can make that comparison piece. The other nice thing about it is they'll go back to something from before. And not every time, but most of the time, if they're simpler ones, they'll go back to a couple of the easier tests. I think the geometric and the P are probably the two quickest. Nth term test for divergence, I think, is pretty quick. I told you before, an integral. I don't mind doing an integral test, but I'm only going to do it if the integral looks easy. I'm not going to do parts or something. Okay? But if I'm catching something like this, I remember that P series, I'd rather do that than an integral test, even though it would still work just fine. Okay? You've also seen that sometimes like the partial sums take a little bit longer. Not saying you'll never need them, but they do take a little bit more time. So if I can find a quicker one, I will. Okay? And the comparison is nice because either one you do lets you go back to one of those quicker ones because you're reducing that series down. That makes it a little bit better. Okay? Now remember,